It's always good to see smallish models around 1 billion parameter mark. The reason why I'm so excited to share this model, GAP 1.3 billion, is that it's a newish model which uses a lot of new techniques and still it utilizes handful of parameters. Recently, all of these large language models such as ChatGPT, Claude, Llamas, Mistral, they have demonstrated really impressive capabilities, and in some cases they have even surpassed human level performance in several tasks. But despite of their success, the resource intensive demands of these models requiring significant computational power for both training and inference limit their deployment to edge devices, commodity hardware, and even to the high performance servers. Even if you try to deploy a biggish like 70 billion model on a huge P AWS cloud instance, you won't be able to do it because it still requires multi-node cluster, multi-GPU cluster, and it is quite expensive. Also, the extensive calculation requirements of the models often lead to increased latency in response times. With the increased need for LLMs to operate efficiently on CPUs, research about lightweight models that are optimized for CPU inference has emerged, and the good thing is that we are observing more and more these smaller models. And this new model, GAP 1.3 billion, is a lightweight LLM trained on 550 billion tokens in both Chinese and English languages. The good thing about this model, or should I say unique thing about this model, is that it uses a lot of new techniques such as rope, group query attention, and flash attention to accelerate training while maintaining model performance. Also, they have fine tuned the model using 10 million samples of instruction data to enhance alignment. This model shows outstanding performance on general benchmarks such as MMLU, CEVAL, and CMMLU, outperforming comparative models such as Mind LLM 1.3 billion and Tiny Llama 1.1 billion. Also, the FP32 version of this model achieves commendable inference times on CPU, with ongoing efforts to further enhance speed through advanced quantization techniques. So, I think that the release of this GAP 1.3 billion model as an open source model marks a significant contribution to the development of lightweight LLMs. Now, coming to the unique things which this model shows, let me touch a little bit on those techniques. First, the architecture of this GAP 1.3 billion is grounded in Transformers framework, and yet it incorporates several advanced techniques such as it doesn't use the usual tokenizer, such as original Llama tokenizer due to its suboptimal tokenization efficiency for Chinese tasks. By building upon the ChatGLM3 tokenizer model, they have developed a new vocabulary containing around 65,000 entries. And this is different from the vocabularies of UN and Baisha 2 model, which both exceed 100,000 entries and are deemed too large. The rationale behind this strategy is to utilize a more compact vocabulary, therefore reducing the number of model parameters. And this approach enhances the model's inference speed without sacrificing its performance. Another new thing is that they have employed an untied embedding strategy, diverging from the conventional practice of tying the weights of the input embedding to the output layer. This choice, though increasing memory requirement, is justified by the resultant performance case. Also, they have used rope or rotary positional embedding. If you don't know what that is, I have done a detailed video in a very simple words, so please search the channel with rope. Anyway, in this model, the rope serves as their primary mechanism for incorporating positional information into the model. And this approach is now being used more and more. And they have also utilized FP32 for generating position IDs, which prevents position collision. They have also modified to, transformer blocks to optimize training efficiency and stability, and they have also used group query attention mechanism rather than the conventional multi-headed attention, and that actually significantly enhances inference speed without detracting from accuracy by grouping the heads of k and v to share a singular queue. And then they have also used swigglue activation function, which is a hybrid of swish and gated linear unit that is used for efficacy. Also, The infrastructure wise, they have done a lot of great things. They have used the AdamW optimizer, and then they also have, due to the CUDA memory constraint, they have also established a global batch size of 320 samples, accommodating a model sequence length of 4K tokens. And such a small batch size makes training unstable, but what they did was they implemented batch sample replacement and then few other things like skipping specific iterations. They also implemented embedding layer gradient shrink, and for alignment they use supervised fine tuning and direct preference optimization and a lot of other cool things. I will drop the link to this model card in video's description. Play around with it. This is in Chinese, but translate it into Google and you should be able to play around with it. Also, one thing I wanted to tell you that I tried to run this model by using this these commands, but it didn't work. Maybe because it is not compatible with the latest version of Transformers, so maybe we just need for Transformers library to support this. There are a lot of conflicts and stuff with this one, so unfortunately I was not able to run it. I have even downgraded my torch, I have downgraded, upgraded a lot of things, but didn't work. So and if you manage to get it working, please share how did you do it, because with the current and previous version of torch, Transformers, deep speed, it doesn't work anyway. But nonetheless, I think a bilingual model in circa 1 billion parameter mark, always good idea. That's it, guys. Let me know what do you think. If you like the content, please consider subscribing to the channel, and if you're already subscribed, please share it among your network as it helps. Thanks for watching.